All right, cool kids. So we're talking about the FRQs that were due today. I'm going to go ahead and close this down really quickly. You were to attempt 2 different FRQs, and I have the answer keys to both, the AP answer keys. I'm giving you a quick introduction to FRQs, and I'm going to basically give you all week, listen carefully, I'm going to give you all week to not only finish attempting it on your own, if you haven't already, but to also go check out the answer keys and grade it with a colored pen on your own, just to see how you were able to do. I'm going to give you until Friday to not only finish attempting it if you need to, on your own with a pencil, but to also get a colored pen and to check. I'll show you actually it in your folder tomorrow, but I'll also email out. Thanks, guys. I'm just going to drop it off. But to also grade it as well. So I'm giving you a few intros, a few pointers, and then you guys are going to go check out the answer keys. David, sorry, go ahead.
I was just going to say, so if we already finished, we should check it.
Yeah.
Could we turn it in there?
You can turn it in the back tray whenever. I'm just saying by Friday. That way it's not like necessarily due tomorrow because we're going to use chapter 3 today. Okay, so with this FRQ, or with both of the FRQs, every AP FRQ has 9 points. So theoretically, if you have your FRQ, you could be looking at this really quickly. I wouldn't necessarily try to grade it right this second. But every FRQ has 9 points. So if you look over here on the right side, you get 1 point, 4, 2 points, 3 points, 4 points, 5 points, 6 points, 7 points, 8 points. Wait a minute, where's the 9th point? 5, 6, 7, 8. Wait, where is the 9th point? 5, 6, 7. What?
That's a fake one.
No, it's not a fake. Oh no, did I cut something off? No, I didn't. What's missing? Units are missing. Stink. I must have cut it off. There's a point for the units because it's not up there anywhere else. That is so weird. Okay. Usually. I'll get a better picture of it. Obviously, something went wrong, and the units point, I think it was probably right here at the bottom. Somehow I cut it off. I don't know how. Maybe it was underneath the line. So there are 9 points total. Sorry, the units point would make number 9. And so what you do is in every question, there is a proper way of solving it. Now, really quickly, do you guys see how this one says 125 over 12 pi? You could have stopped back here when you just plugged in. You do not need to simplify. You could have stopped right there and written the units, and you would have been fine. So when it says find the volume when h equals 5, it just means find a proper representation of volume. It doesn't have to be in the exact fraction. It could have been a decimal. It could be in this form. It just needs to mean the same thing, to equal the same thing. But the units, that last point, the centimeters cubed, if you didn't write that down, you would not lose a point here for finding the volume. This is just the number. You would lose a point down in the units. Now up here, they do have, if you notice, there's a one where it says an or. It says either get volume all in terms of one variable, which means substitute before deriving, or you could use dRdt and substitute after deriving. Down here it says chain rule or product rule error. Chain rule or product rule error. If you're supposed to get 2 points for finding dv dt. If you didn't do product rule, you don't get any points. That's what that says. For this step, finding the derivative, if you didn't do product rule, you don't get any points. And then the final step is evaluation. Once again, you might have the 15 over pi, but you might have a decimal, or, look, you might have boxed it. Look at how much time that would save. Because this one is non-calculator. You could have boxed it with the units. You do not have to simplify. You just have to have something that means the same, or equals the same. And last but not least, it shows you 2 points total, 1.4 and 1.4. So I want you guys to do the best you can by Friday to go ahead and grade these. I'm not saying it's going to be easy, and you might have questions, and if so, then go ahead and you can put a little question mark and actually write in color pen what the point was for, and then when I look at it, I'll see whether or not I think you got it. But we will go ahead and talk about this on Friday. I'm giving you guys plenty of time to try it out. And to see what you're able to grade. If you want to come ask me questions during lunch after school, being like, hey, did I get this point? I can pull up the answer key and check. But I'll get you a better answer key because obviously that last one is missing. Okay, there's the other FRQ that you have. I have a similar answer key. It also has 9 points total on the outside. What I do whenever I grade your guys' FRQs is every time I see one of those points that you've gotten correct, I put a little check mark. So when you see me grade your FRQs from here on out, if you see a check, you're like, hey, I got a point. Another check. I got another point. Another check. I got another point. An X. I missed a point. Does that make sense? So if you guys want to try to do that same thing, that would be great as well. You can do little check marks every time you identify one of those points. And we'll learn as we go as to whether or not the AP would have given you all those points, whether they see some illegal math, and they might have taken off a point that you thought you might have gotten. This is just an introduction to you guys trying to FRQs and looking at the answer keys and not only trying to figure out what went wrong, if something did, but to also kind of get a feel for what the answer keys look like. So, when's that due again? Friday. I'll get a better version of that answer key and I'll just email it out. Why am I making it Friday? Because I want you guys tonight to be starting on 3.1. Okay? So I don't want to jam-pack it in and give you plenty of time, plenty of ahead warning and notice. I'll show you tomorrow where it's going to be on the Google Drive. It'll probably be under handouts and assignments. It'll probably be under handouts and assignments by the end of today. As you guys are copying this page, for these three pictures, you don't need to worry about the red dots. You don't need to worry about necessarily putting all the tick marks, but what I do need is the curve from -1 to 2, and whether or not the endpoints or the vertex is open or closed. That's what I need you guys to show. Chapter 3, just to give you a quick where are we going, what are we doing. Chapter 3 is all about, well, I shouldn't say that. 3.1 to 3.5. 3.1 to 3.5, which is chapter 3A. (3.1 to 3.5), which is chapter 3A, is all about the graph, aka the behavior of a function, which we can figure out from derivatives, first and second. 3.1 to 3.5, the big, huge picture is the behavior of a function, which usually is easiest to see in a graph. The behavior of a function, which has tie-ins to graphing. Right now, what you guys are writing is about extremes. And if you look at the title, it's extrema. But think the extremes. Extrema are the extremes. Extremes. Max, min, highs, lows. Extremes, extrema. There are absolute extremes and there are relative extremes. We'll have some fun conversations about that. There are absolute extremes and there are relative extremes. Once again, 3.1 to 3.5, chapter 3A, what we're trying to fit in before Thanksgiving is all about the behavior of a function. And as you guys are writing that, I'm just going to kind of go off to the side, just to give you an idea. Just to give you an idea. Let me just use the first graph. Just the vertex. Some of this you saw last year. couple more seconds, but once you guys have it, go ahead and look at the front board.
Carolyn.
Good call. Very good call. As you guys are getting ready, let's look at the front board. Did we talk last year about increasing, decreasing?
Yeah.
We used for decreasing the idea of falling. And we talked about how you should read a graph as you read in English from left to right. Increasing is rising. Concave up, concave down, concave up like a cup, concave down like a frown, right? Okay, that's about concave. And did we talk about minimums and maximums? With what kinds of functions?
Usually like squares.
Yeah, usually parabolas, because parabolas always have vertices, right? But polynomials might have mins and maxes also, and not just x squares. But last year, I did this thing called approximation with anything but a quadratic. Mr. Che would have had to too. You guys tried to graph polynomials. But what we did with last year with polynomials is we would talk about end behavior, whether it was even or whether it was odd. Remember advancements? Whether it was even or whether it was odd, whether the coefficient was positive or negative. We talked about how to find the zeros with factoring, and sometimes it got really nasty with polynomials, factoring, like a quartic or a cubic. We had to test zeros and do synthetic divisions. So we tried to find intercepts, we tried to find the zeros, I should say the y and the x intercepts, which include the zeros. We would try to figure out the end behavior, and then we would do something like make a table to find a few more points to make an educated guess, and swoop, there it was. Kind of. Ish. We approximated. And I said, without calculus, we can't get any more precise than that. But what are we in? So we can get more precise. It's just going to take sections 3.1 to 3.5 to totally get there. But I want to just introduce you to the idea with this guy on the board. Do you guys agree that there is a minimum at x equals 0?
Yes.
X equals 0 is here, right? So then follow the line. Is there a min when x equals 0? Yes. Now y equals something or others, but whatever. There is a min at x equals 0. Okay. Do you agree that the function is decreasing from -1 to 0? Is it going down? Is it falling? Yeah. I don't include 0 because technically right at 0 it's momentarily stopped, and I know this by the slope of the tangent line. The rate or the slope is 0. There's a horizontal tangent. But here, the rate or the slope is negative. And the slope will always be negative when the function is decreasing. That's section 3.2. Nope, 3.3. And so when the slope goes positive, what's the function always going to be doing? Increasing. That's section 3.32 also. At 2, the slope is positive, so I include it. At -1, the slope is negative, so I include it. You guys just learned a whole section. Increasing, decreasing, based on the slopes of the tangent lines. What's this say?
In between.
In between -1 to 2. It's decreasing, then increasing, but what stays the same the whole time? Nope. Anybody know what CU stands for? It is continuous, but concave up. Concave up. It's concave up the whole time, in between here to here. Guess what figures that out? You ready? Mind blown a little bit? The tangent line goes from a negative, a pretty low negative, like -5 or something, -10. And then it goes to 0. Wait, negatives to 0, isn't that getting higher? And then it goes positive. The slopes are increasing, which means the second derivative is positive. Guess what happens when the second derivative is negative?
It's concave down.
It's concave down. That's section 3.4.
Whoa.
Whoa. minimums. That's kind of section 3.1, but it's also kind of sections 3.3 and 3.4. Wait, I don't get it. It's not that hard, right? You look at a graph and it's a parabola. Parabolas are easy to graph. So you say, oh, it's going down, and oh, it's going up, and oh, there's a min. The question, what if the graph was something like this? Lizzie. I don't know. He's at least a 1, 2, 3, 4, 5, 6 degree polynomial. Woo! How are we going to find the minimum to a 6 degree polynomial?
There's a lot of them.
We have to do some calc work. Now, the nice thing is we're not supposed to be learning any new derivatives, any new rules, but we're going to learn how to use calculus to, if it was that bad, get that exact graph. Every single piece. Every min, every max, every concave up, every concave down. Something that I didn't talk about, a point of inflection, which is in between concavities, because I didn't show you a change in concavity, I just showed you one concavity. But guys, section 3.1 to 3.5, when we get to 3.5, the hope is I could give you a super nasty 6 degree polynomial and you could get me the exact graph. As good, if not better, than a graphing calculator, because as we know, sometimes they can only do so. Alright, here we go. To start off this idea, extrema, extremes. Before we even get to what I would call, ooh, guys, is this what you would, just from your life experience? I said this was a min, right? Is this the min of the graph? What do I mean by that?
No.
Why is it not the minimum? It's just a minimum.
If you're having a bad day, this probably would be worse.
That's one way of thinking about it.
No.
But then also looking at the whole graph, if you see the big picture, why was that not the minimum?
This is a lower one.
There are lower ones, right? Ooh, this is a good life lesson for high school. So when there's a bad day, should we act like the entire world has ended?
Yeah.
We can feel the emotions of it, but do we need to maybe think of, hold on, God can see the whole picture and He's going to get me through? And there might be lower times I need to hold on even through the maybe not as well. Anyway, coming back. But you never know. You never know if there's going to be a lower or not in life. But in a polynomial, well, we're going to have to find all the minimums and then compare to find the absolute minimum.
She would learn 3.1 to 3.5 from that.
That would be cool. Actually, there is a blog, and I'll have to find it. It's been a while since I've read it. But she basically compared like the increasing, decreasing, and the extrema to life, and it was. I mean, it wasn't funny. It was sobering, but still. She was like life lessons about all of the extrema. Anyway, absolute means the lowest for the entire, or the highest for the entire. D min, D max. For that one, what would be D min? I kind of think the one over there is a little bit lower than the other one, right?
Yes.
Okay. Mathematically, we just find them all and test them all. It's literally like a testing game. But for right now, just to visualize, why does this one, which is continuous on the closed interval, where does it have its minimum? At the vertex. Where does it have its maximum? At an endpoint. So, min at a vertex, max at an endpoint. Oh, this one, where's the min? At the vertex. Where's the max? Why is there none? If it's not there because there's a hole, okay, fine, it's open, so I can't have it at 2. Why wouldn't it be at the one right before? What's right before 2? Give me a number.
1.9.
Ah, what about 1.99? Give me another number.
Okay.
What about 1.99? Is there any one point right before 2? No. So does it make sense if there's a hole at 2, I have to say no max? How would I know that? Find the height at 2. It's the highest. Okay, cool. If it's not included, I just say none. So there is a min, no max. It's going to keep on getting higher and higher and higher.
Wait, so if there's a hole, there's no max?
If there's a hole at what would be the max, then there's no max. Okay? What about this one? What's the max? What's the min? Oh. It's a piecewise function, and they moved that guy. Well, that would have been the min, but he's not there, so therefore, alright, not a min. Terrible.
Is there no
Is there no way to like mathematically represent that the maximum is getting infinitely close to 2?
We could say the limit of the function is x approaches 2, but the problem is that it's not actually, well, not 2. X approaches 5.
Mm-hmm.
But we wouldn't state that 5 was the maximum. We could say that it's bounded by 5. But we couldn't say that 5 is the max since it's not clear. Now guys, what's the difference between having a max, having a min, and not having a max or not having a min? What showed up in these ones that made me say, oh, no, there isn't one? Or discontinuity in general. So, that leads us to the following. Well, that's fun. I actually think I didn't orient it this morning. Oops. That leads us to the following idea. Okay. Following idea. Relative or local extrema occur at the highest and the lowest values contained within an open interval. Now that's just an idea. What I just talked about with the discontinuity showing up. We saw when there would be a max and when there would be a min. When there wouldn't be or when there might not be. But here are a few more functions. Guys, don't worry about getting down the equations. Just get a quick sketch of them. Here are a few other functions that look a little different, not just parabolas, but other things as well. A rational function, an absolute, a trigonometric function. Relative or local. Relative or local extrema occur at the highest and lowest values contained within an open interval. Meaning it doesn't need to be the very highest or the very lowest on the entire function. It just has to be a highest, a lowest of a certain portion of the graph. Which is what I tried to show you on the board. Relative or local extrema occur at highest, lowest values contained within an open interval. There's actually a theorem that's going to help us with the absolute. Absolute, to be honest, are harder to find than relative in some ways. It's relative, it just needs to be true for a certain region. Oh, local. That makes sense. Local. Just for a certain area, right? Just for a certain portion, just for a certain range of or domain of x values. So the highest, the lowest does not need to be the highest or the lowest of the entire function. When will relative extrema always occur? When will you have a highest or a lowest for a certain open interval, which means you have to have some space to the right of it and some space to the left of it, and it has to be the highest or the lowest in that interval. Well, my hint is that calculus is going to help us with all of this. And I already kind of hinted towards the tangent line. The derivative is the slope of the tangent line. So my question is, can you guys tell what kind of tangent line is going on at 3-2?
Oh, no.
It does look like it might be going negative, but technically.
It's probably how
Oh, that's fine. The orientation is on. F prime of 3 equals 0. It's a horizontal tangent. It's kind of hard to see, but if you did the math, I promise you, F prime of 3 equals 0. Take the derivative and plug in 3. This one, it's a relative min. It's the lowest for like a little region all around it. If I was just to like circle a region, this one, circle a region. It's the lowest of a region containing it. An open interval is what they say. Uh-oh. What's the derivative here? It's undefined because it's a sharp point. The tangent line says one thing from one direction, another thing from another direction. The limit does not agree, so the derivative does not exist. The limit of this tangent lines. What are the slopes of these ones?
2.
Yeah? F prime of, if you were to take the derivative and plug in pi over 2, or plug in 3 pi over 2, both of those would be 0. If you were to plug in pi over 2 or 3 pi over 2, both of those would be 0. Wait guys, think about the quadratic on the page before. What would have been the slope of the tangent line at that minimum? 0. Wait, look at this one up here. What would be the slope of the tangent line at that minimum?
0.
Wait, what about this maximum?
There seems to be a...
What's the slope at this minimum? What about this maximum? What about that minimum? Anytime you have a smooth turn, the turn happens at a low or at a high, at a relative min or at a relative max, and the slope of the tangent line, if it's a smooth turn, will always be 0. What if there's a sharp turn? Or a sharp turn? There will always be a min or a max at a sharp turn, and the derivative will always be undefined. So how do we find relative mins and maxes? Got a calculator. It's as easy as find the derivative and find the zeros and the undefineds. You just learned struggle. Critical numbers. Definition of a critical number. Let a function exist. First key, it must exist. Remember the hole? There's a hole, we have some serious issues. So the first key, a function must exist. A function must exist. But the derivative will be 0 or d(n). A critical number is defined to be an x value for which the function exists. C are the critical numbers. That's what refers to critical numbers. So a function has to exist there, and the derivative has to equal 0 or undefined. They can be called critical numbers. They can be called critical values or points. And my hint is if f prime equals a numerator over a denominator, if f prime equals a numerator or a denominator, we can always find the zeros by setting the numerator equal to 0. You can always find the undefineds by setting the denominator equal to 0. AKA HTL's horizontal tangent lines will be on top. Sharp points or vertical tangent lines will be on bottom. More vertical tangent lines than anything. And if the function is not a rational function, if it's not a numerator over denominator, no big deal. Just set it equal to 0, and if there's no denominator, there are no undefined points. Not every derivative has DNEs. We know sometimes the domain is all real numbers, so who cares? But to find critical numbers, we need domain. To figure out when f exists, and then we need to find the derivative. And then we need to find its zeros and its undefined. Now, kiddos, can it sometimes take some work to find a derivative? Can it sometimes take some work to find a derivative? Yes. So the struggle on 3.1 to 3.5 is we're going to have to practice, and to practice, we're going to have to find first and second derivatives that sometimes take a lot of time, and that's only the beginning of the problem. So now you see what you're going to start over. This is what, remember? 19? 19. You get either 19 or 20. Someone can double check. Maybe. So let me show you a picture. Critical numbers. I'm going to go ahead and dual screen it for those of you that might still be writing. Let's see if it works on the following. Let's see if it works on the following sketch. Now, I haven't even given you x values to make it complicated. I just gave you a quick sketch. It's starting from a low point. There's a smooth turn, sharp turn, lots of different concavities. This would be fun to talk about increasing and decreasing for. But my question to you is, if I was to go ahead and just make a quick little, make that to be an A. And then we just letter them all the way through. My question to you, struggle. Alright, we're just going to leave this off for right now. It's totally done. Oh, you're killing me. Question. Where's the absolute min?
At very bottom left.
At very bottom left. Good. Is there anything special about his relative, about his derivative? What's the slope of the tangent line there?
Positive.
It's positive, so that's not special, but he's an endpoint. What's this one?
0.
So he's going to be a relative. What's the only way that we would find him? Taking a derivative equal to 0. That one's a 0, that one's a DME, that one's an endpoint. We've just learned to find stroma. You guys can find that. We're going to have to test endpoints if there are any, but we're going to have to also find critical numbers. Alright, cool kids. Tonight might be a good night to start 3-1 if you can. It's not a bad idea. But if not, get that thing graded and get it out of your life, okay? It'll be in your email and it'll also be in your Google Drive. It'll be in your email and it'll also be in your Google Drive. And are those points missing, Zach? Have you had that? I'll go into it. You can come get homework spirals after school, kiddos.
好傻逼啊！不知道为什么每一次那个写律字，我好多人每一篇都跟写4行，老师都直接给我满分。真的是。
Okay. Sorry, kid. Are you feeling better?
Yeah.
That's rough.
CMSD.
See ya.